homework side. So we are going to continue the discussion for progression, and progression has been done already. Regression is what we're going to do. And before I forget, tomorrow's makeup class would be in room 210, which is just half a floor above, you know. So and basically it's from 10 to 11:15. So I'll be there like 10 minutes before to make sure that the door is open or something. I'll be from 10 to 11:15. And then if you can't make it, then as I said, I hope enough people show up so that I won't have to talk to the walls. But if you can't make it, there will still be the video that will be posted. Okay. Questions? Okay.
Professor,
Yes.
how many points is the homework?
How many points is the homework? Basically, it will be about 5 percentage points for each homework. Okay, and yeah, that's how it is, and that's what we've done in the past. Okay. And there it's like, I think homework is where you can be asked. We can ask questions that take more time, and you'll try to figure out how to do things and so on. Exams are obviously fixed time, and I think the homework is probably more representative of what you should be able to do if you really understood this course than the exams. Because exams, unfortunately, if they are in class, then there are certain questions I can't ask because it takes just too long. That's what I think. Okay. Any other questions? Okay. So clearly a lot of people are doing homeworks at home or have dropped the course. It's mostly not for the benefit of you, but for the people who if you ever are in a situation where you're not done with the homework and you miss the class to do the homework, that's a dumb idea. If you show up for the class, you can always take an extra hour to complete it. But missing the class as well as being late on the homework, as far as I'm concerned, whoever comes afterwards is late. Okay, so if I'm strict, that's what it is. So I think don't lose sleep. It makes no sense. Okay, so I was discussing. We already discussed the progression. Thanks. And then the regression is what we were about discussing. But since we are discussing progression, that here is a completely different artificial example. Okay, I mean this one has actual semantics, right? This has you tended to think that clear means a block is clear, on means there's one block on top of another block, etc. But this model itself works as long as your initial and goal states are in terms of state variables. Okay, so in fact, the homework that I added for the planning problem, that is essentially more like this. So I just basically made an artificial domain. Okay, so this could mean something in some domain, but this is a a Boolean variable P, Q, and S. Here is a Boolean variable R and S. Okay, so I want to just do for this. Okay, so in this case, this is the initial state. This is the goal state, okay, and here are the operators I have, okay, and the assumption in this writing is anything below means it's a precondition, anything above means it's an effect. So this is preconditions, and these are effects. Okay, so you have actions, and you have preconditions, and you have effects, right? So let's see. So if I start with, if I'm doing progression, if I start with the initial state, is P, Q, S. Okay, tell me what can I progress? What actions can I do from PQS?
A1
I can do A1. If I were to do A1, can I do A1?
Yes.
Yes, because its precondition is P is holding, right? And if I were to do A1, what do I get? I must write R and not S, right? And then as far as the other stuff, P and Q just get copied over. right? Because the idea is, in fact, if you look at this entire description, you realize that the number of state variables are P, Q, R, S, J, T, M. Because I mentioned them somewhere, right? So if I mention them, it's part of the problem. So this particular problem has P, Q, S, P, Q, R, S, J, T, M are the variables, which essentially means that there are 2 power 7 states that you can represent in this case. Okay, now how come I did not say anything about JTM in the initial state? What is the value of J in the initial state? False. I did say it. I just told you what are the true ones. Everything else is false. That's the assumption, right? I mean, initial state is completely specified, and so if I didn't say it, then it is actually said to be negative. Okay, so that's why actually it works that in this state too, J is false, T is false, M is false. Because if you start from a complete state and you apply a deterministic action, you get a complete state. Right? Now, of course, I wrote not S here. Actually, I can remove not S too, because writing not S is not needed. You don't have to write the negative ones. Okay, so that's for A1. So basically, A1 gets you to PQR. Okay, now, and then what about A2? Can I do A2?
No.
No, I can't do A2. So there is no branch for A2. Can I do A3?
Yes.
Yes. There is a branch for A3 because Q is available, and in that case, it writes S, not T, M will be written, and on top, so S, not T and M, and then P and Q. Right? Okay. P, Q, and of course S is already there. Okay. Now, so it's P, Q, S, not T, M, and so again, not T can be removed. It's useful to write the not T in the beginning if you're doing this as examples, because T is no longer allowed to be copied over from the previous state. You can't copy over a variable whose value already has been clamped by the action. Okay, so that's it. So this is S, T, M, and so then now that I have everybody here, I can remove S, not T. Just for just convention's sake. There's nothing wrong in writing it. Yes.
If in the initial state T is false, and this action actually executes not T, it results in not
That's
T.
an interesting point, actually. In fact, for now, let's assume that I just basically, whenever I do it, I will make sure that T is false. Okay? That's basically what I mean. So, irrespective of so in fact, that kind of an action is useful if you did not know what the value of T was to begin with. And yet, after this action, you will know what the value of T is. Do you see what I'm saying? I mean, so if I may or may not know whether somebody is sleeping, but if I yell saying, "Are you sleeping?" then I know what the answer is, because they will be awake after that. Right? So sometimes, if they're awake, they're still awake. If they're sleeping, they're awake now. So that's basically, sometimes that sort of thing helps. Okay. But as far as our thing is concerned, yeah, you didn't do anything different. It said not T, and it was not T before too, so it didn't do anything inconsistent. Yes.
Is the goal state something that contains RNS or solely RNS?
What the goal state is, whenever R and S are true, then it's a goal state. That's it. Anything else, extra details. That's fine. As long as R and S are true, then that's fine. If you want other things not to be true, then you need to state that. That's a reasonable thing, right? No. So anyway, then basically that's what you had. And then so you have those two states, and then you can continue if you want. So in this particular case, if I am in this state, I can ask, is it a goal state? It's not a goal state because R and S are not present. R is present, but not R and S. This is not a goal state because R and S are not present. S is present, not R. Okay? Now, however, if in fact I now continue and I do from, suppose I happen to pick this state for some reason because of a star search telling me, remember that, now G equal to 0 here, G equal to 1 because assuming all actions have the same cost, G equal to 1 here and G equal to 1 here. Okay, now I did not yet tell you anything about H, but I did mention towards the end of last class that one reasonable heuristic is to think of the number of missing goals. So the H value here equal to 1 because it's missing S. And the H value here is also equal to 1 because it's missing R. Right? Okay? So then F value equal to 2, F value equal to 2. Okay, so both of these are in the queue, then you pick one of them. Suppose I just pick this, then I could expand it. I mean, when I picked it, I checked is it goal or not. If not, I expanded it by basically considering all possible actions that can be done from it. Okay, so basically I could, in one of the actions I will do from there is, one of the actions I will do from there is A3. Right, because I consider, I'm thinking in my head. One action I can consider doing is doing A3 because A3 will be applicable. Okay? And then what will it do? It will give me S, not T, M, and then P, Q, R. Okay? And of course, not T can now be removed. Right? Now at this point, this is a goal state. Okay, in fact, it's G value equal to 2, H equal to 0, so F equal to 2. So if you're lucky, you are actually likely to pick this before this, and you'll be done. If you're unlucky, you will pick this, go somewhere further, and then finally you'll pick this, and you'll be done. Right? Okay? So that's basically, I'm doing search using progression. It just looks like normal A-star search. The only difference is previously I would call some child generator outside of my program's control saying, please tell me who the children are. Now I have everything in front of me. So I can look at the actions and see which actions are applicable, which are not. Not only that, I can also tell myself how far am I from the goal state, for example. Here it's a simplistic idea. I assumed that my distance is just the number of missing goals. But no more simplistic than my distance in the 8 puzzle is the number of misplaced tiles. Okay, we'll think of better outcomes. Okay, so that's basically for progression search. Okay, so now what I'm going to do is I set this idea that we can also do digression search, right? And in the case of digression search, the interesting idea is that of course you are trying to ask. Basically, in this case, remember, in this case, the plan, if you were to be done here, then what's the plan? The plan is A1, A3. That's the plan. Right? So you constructed, so if you stop here, each of these are the prefixes of the possible prefixes of the final plan. Prefix, the beginning part of the final plan. Okay? And when you complete the full plan, then basically you just take that. That's what progression search is doing. Regression search will try to look at possible suffixes of the final plan, the ending parts of the final plan. And a suffix is a full plan if in fact the suffix can be directly executed in the initial state. Just as a prefix is a full plan, if you execute the prefix, you will be in the goal state. Right? Okay? So we are trying to look at suffixes. And when you're thinking of suffix, when you think of the prefixes, you're thinking of what can I do from the current state? Okay, what can be done? Here I'm asking, what would be the last state? What would be the last state? What would be the last action I'll be doing if this is where I want to be in? Right? Okay. And I considered, now of course the question is, suppose put down A, stack A, B, put down B, the minimum requirement essentially is for an action to be the last action, it better be the case that it's not doing any harm. That's the minimum requirement. It's like the Hippocratic Oath. Doctors are told first do no harm, right? So similarly, if you are the last action, There's nothing after you. If you just killed one of the goals, then that's it. That goal is not true. There's nobody who's coming after you to fix it. Right? So if this guy's effects are inconsistent with what you want, that means it's actually killing one of the goals. Because when this action happens, so when put down A happens, basically on table X must be true after it, and hand empty must be true, clean X must be true, not holding X must be true. Okay, so if any of these are directly inconsistent with this, you don't want it as the last action, because there is no way that can be the suffix of a correct plan. Right? So unlike here where you said it cannot be the prefix of the current plan if it can't even be executed in the initial state. So you check whether the preconditions are true. Here you are checking if the effects of the action are consistent with the goals that you want. Only consistent. If they're inconsistent, that means they're actually killing one of the goals that you want, they can't be the final action. Right? Okay? That's why I asked, can you do put down B? And I think you said, no, you can't do put down B last time. Why? If I were to put down B, then put down X will give clear X as one of the effects. So put down B will ensure clear B after it is done. But you wanted clear B to be false, not true. So if this is the last guy, you're dead. So just as we didn't consider A2 in progression, you won't consider put down B in regression. So first do no harm. The second thing is, if you don't do any harm, that only means, so as I said, my garage example, I go home, I'm supposed to reach home, so I'll reach home, but I won't get out of my car. I'll keep doing all sorts of redundant actions, such as, eating candy or something. That's not inconsistent with what I need to do, but neither is it useful. So first do no harm, and then at least do something good. That's part of the Hippocratic Oath too. It's not enforced as much as, first do no harm. So don't just open up people just to see how they look inside, okay, and then sue them back, okay? So you better have some reason why you open them up, right? And so if you are doing this action, first it should not do any harm, and then it should also do something good. What does it mean to do something good? In our little language, it better be giving either this or this. Otherwise, what the heck is it doing? The only thing I care about in the world, according to this problem, is that B should be not clear and hand should be empty. If you can't give any of them, I'm not interested in you. But even if you give one of them, if you're killing the other, I'm not interested in you. Okay? Now, these two guys satisfied those conditions, so I go back and I will allow them to enter the search space. Now the question, of course, is what is the state here? The state here is if this guy is already giving one of these variable values. So for example, put down A will give hand empty, right? If you put down A, then you will get hand empty. So you no longer need to get hand empty. So of the two goals you needed, one is already satisfied by this guy. So whoever comes before him or her need to just satisfy not clear B. Not clear B. Looks like some progress has been made. We had two sub-goals, now we only have one sub-goal. However, this put down A has its own maintenance. You can't actually do put down A unless its preconditions are satisfied in the state before it. Do you see what I'm saying? And so, not only must you have not clear B, before put down A, but any precondition of put down A better be present here. And to put down A, all you needed, thankfully, is holding A. So I put holding A here. So all I just said is if you originally wanted to do not clear B and hand empty, if you decide to make this as the last action, then you just need to work on not clear B and holding A. That's it. And similarly, if you do stack AB as the last action, then you essentially can say again, stack AB will give not clear B. Because if you put A on top of B, B is not clear. Again, I'm not asking you to understand, obviously I'm also appealing to your intuition about blocks world because you do have one. Okay, but really what your program knows is not what blocks world is, but what is written here. Right? And your program basically says stack AB. If you were to do stack AB, stack XY will give you hand empty. Sorry, stack XY will. This is stack XY. Yeah, stack XY will give you not clear Y, so not clear B. Interestingly, it will also give you hand empty. So if you do stack AB, you're done. No more top level goals are required anymore. No more of the top level goals are left. But then, to be able to do stack AB, you need to work on its preconditions. You cannot stack A on top of B unless you're holding A and B is clear. So I wrote those, holding A and clear B. Okay? So that's how the thing is extended. It's a little more unnatural compared to going forward, but it's not that hard to figure this out. Okay, so this is what I wrote here. You can look at it at your leisure. A state S can be regressed over an action if and only, this is called regressing. Okay, a state S can be regressed over an action as long as this is first do no harm, which is there is no variable V such that V is given a different value by the effect of this action and the goal state. If so, then you're dead. Right? You can't use that as the last action. That's first. Secondly, do something useful. There is at least one variable V dash such that V dash is given the same value by this action and this goal state. In which case, it's both not doing any harm and is being useful. At which point, you can compute the new state by copying over any of the sub-goals that are not given by the action. Remember, action should have given at least something useful. So copying over everything else that's not given by this action, and then appending to it all the preconditions of this action. So now those become your new sub-goals. Right? This is in some sense cognitively plausible way of doing reasoning. I need to be at my home, so I will get out of my car at my home. Now, to be getting out of my car at my home, I should be in the car to begin with. And the car should be at home. So I just kind of do backward reasoning, but then execution will be done forward way. Okay, now when do I stop? When I'm going like this, when do I stop? What's the goal test? Anything I want, if it's already true in the initial state, think about this as your wish list. So there was a top level wish list. That's the problem's wish list. When you sub-goal using this action, you now have a separate wish list, hopefully cheaper wish list. Okay, if this was already true in the initial state, you're done. You shouldn't be wasting your time searching anymore. Whatever I wanted is already true in the initial state. If not, then maybe this is true in the initial state. That means if in the initial state holding A is true and clear B is true, you're done. Okay? So in some sense, essentially in the progression, the initial state is being progressed. Step by step by step, until it becomes the goal state. In the regression, the goal state is being regressed step by step by step, until it becomes the initial state. Or at least whatever it wants is already true in the initial state. Notice that the initial state may have many more things that are true. All I care is, do you give me holding A? Do you give me clear B? If so, I'm done. So that's your goal test. Okay? So goal test is stop when everything in the state, current S state S dash, holds in the initial state, Si. In which case, you're done. At which point, the path is, the reverse of the path is your solution. Because this is the final action, and then this will be if there is one more action, then this will be the last but one action, this will be the last action, and so on. Because you just computed a suffix, the complete suffix. Right? Okay, so, now again, as I mentioned last time, regression is actually a much cuter idea than progression in some sense, because it would be harder to do regression in the atomic states, because if you'll have multiple goal states and you have to do parallel search from each of them to see which of them will reach the initial state first. Here in some sense, you're able to do all of that in one fell swoop. That's the reason. In fact, you can think of regression essentially as a search in the space of sets of states. Search in the space of sets of states. Not in the space of states, but in the space of sets of states. Did anybody see a problem with this? When was the last time we talked about search in the space of sets of states?
That was when we were doing blind search.
Exactly. And did we feel like that is like a bug or a feature? If we have to do search in the space of sets of states as against in the space of states, would our life be easier or harder? Way harder, right? Because if you remember, if you have if you have v state variables, Boolean state variables, there are 2 power v states, 2 power v sets of states. How can I say both that regression is a better search and that it searches in the sets of states, space of sets of states? Okay, on one hand, you can actually see that regression should be a better search in the following way. The informal argument is, when you wake up in the morning and you wanted to come to this class, after all, that's your real goal every day, on the days of the class, okay? Now, if you're asking yourself, what should my plan be? And if you started doing progression, there are 1.5 billion actions you can do. For example, you can twiddle your finger. And you can open your eyes and close. That's an action. You can dance. You can put on one shoe. You can have coffee. All of these can be done. Okay? But which of them should you consider doing? So in essence, if in a real enough world, if you are considering just the actions that can be done, that is a humongous number of actions. Just considering that because you can do it basically makes the search space have a huge, huge branching factor. If on the other hand you're going in the backward direction, I know that I have to be in the class, so should my last action be dancing? Should my last action be twiddling my fingers? Should my last actions be having coffee? None of them would be useful because these guys will kill them all. Do you see what I'm saying? So it looks like regression should be good. Your branching factor coming backwards is significantly smaller than the branching factors going forwards. There are many search spaces where branching factor one direction would be much different from branching factor another direction. Suppose you're trying to figure out, given a big human family tree, okay, whether X is an ancestor of Y. Which would you rather search? You can start from X and see if Y falls as a descendant somewhere. Or you can start from Y and see if X will be an ancestor. Which would you rather do? Backwards, because all of us only have 2 parents. And some of us are particularly productive and we have many, many descendants. Right? Our branching factor going down is basically, unless your government sort of puts limits on it, our branching factor going down has no limits. Our branching factor going up is 2 for all humans. That's why I said humans. I don't know what happens in other places, but biological parents exactly 2. Right? It's the same search space, but going backwards, low branching factor, going forwards, much higher branching factor. And so, clearly, since the blind search, if you're doing blind search, B power D is the amount of search you do. Going forward, B is much bigger. Going backward, B is much smaller. Remember, this is obviously a directed or undirected search space.
Undirected.
What?
Undirected.
It's an undirected search space? It's directed. In an undirected search space, branching factor cannot be different in both directions. It has to be. No, you have an asymmetric relation with your father. I keep telling that to my son, that you have an asymmetric relation. I'm your father, you're my son. not yet, we are not equals necessarily. We, it's not, the relationship is not both sides. It's a directed relationship. And that's the only way you can have branching factor less or more compared to the other way. Otherwise, it will be the same in both ways. Okay, so anyway, so regression essentially is saying that you can have lower branching factor in the backward direction than the forward direction. So that's like a strike in favor of regression. Okay, so actually, so this is basically I'm doing this right now. So progression versus regression, who is winning? Who is the better idea? Okay, so what I basically say is regression has lower branching factor. Coming back, you have fewer things that are relevant. Going forward, you do it because it can be done. I mean, you consider doing it because it can be done, not because it's necessarily relevant. Okay, this argument, by the way, is for the blind search, right? If you have a rich uncle who tells you exactly what action to do, then it doesn't matter. The branching factor is only for people who don't have rich uncles. We'll tell them exactly what to do. Okay, so in the case of blind search, which is what you would do if you have no good heuristics, regression has a lower branching factor, progression has a higher branching factor. So it looks like advantage regression. Right? But then regression searches, progression searches in the space of complete and consistent states. If there are V variables, at most there are 2 power V states, at most. Many of them may actually not even be consistent. In the sense, no action will get you to that state, so you would never consider it because you won't reach it. Do you see what I'm saying? I mean, so basically, you barely ever consider while going forward, the possible state where you're dead and you're dancing. Because that's not possible. There is no action that you can imagine which will allow you to be both dead and dancing, unless you're particularly imaginative. Right? Whereas coming back towards, hey, it's a wish list. I would like to be dead and be dancing. So I don't know, maybe there's a way. And I'll keep trying to do that. And then, I'll give up because I will never reach the initial state, which will satisfy these conditions. Right? So in the case of progression, searches in the space of complete states, there are only 2 power V complete states. In the case of regression, it searches in the space of partial states. Now, are there more partial states or complete states? How many of you have done any computer science? No, then you should know. Partial states, there are more, obviously, because every complete state is a partial state. Not every partial state is a complete state. Just from that, there are more partial states. How many more? If there are n state variables, in trying to decide how many states you can construct with them, n Boolean variables, in each state, each variable can be either true or false. 2 times, 2 times, 2 times, 2 times, 2 times, n, so 2 power n. If you're talking about partial states, you may want it to be positive in the goal state, this variable to be positive, one possibility, negative, another possibility. You don't care, third possibility. So now for each variable, there are 3 possibilities. So 3 times 3 times 3 times 3, 3 power n. Right? So in fact, regression is searching in 3 power n sized state space, but it has lower branching factor. Progression is searching in a 2 power n size state space, but it has a much higher branching factor. Now you tell me who wins. Not so clear. Right? I mean, what you did learn is trade-offs in search. Okay, now here is the interesting thing. Why are there 3 power n partial states? I mean, what if there are 3 power n partial states, but somehow you never reach any of the partial states that will not eventually reach the initial state? Then you will be fine. Somehow if you only wish for things that are actually doable, who does that? Do we always wish for things that are only achievable? Of course not. We always wish for crazy things. Okay, so here, this search tree, is it wishing for things that it cannot actually achieve?
Yes.
So that's a bigger form of copy of this. Here, in this search tree, this is one wish list, this is another wish list, that's another wish list. Knowing Flux world, because you are smart people, do you see that there is a wish list there which cannot actually be ever satisfied? The fact that not enough of you are saying, of course we can see, tells you that it's not easy to check whether or not something cannot be satisfied. Okay, tell me somebody who did see, who did see that something cannot be satisfied.
First one.
Which one?
Not clear B and holding.
Not clear B and holding A. Why not?
If there are only two A, B, and then it's possible.
This is a problem with two blocks, one hand. You are bachelors in computer science, junior and senior. You're very smart. It still was not obvious to you when I put these that this is a dead state. In this problem, there is no way, if you only have two blocks on one hand, and if you're holding one of the blocks in that hand, then B has to be clear. I mean, once I explain it, of course it's obvious to you. Right? And if it's not obvious to you, how come you expect your program to figure this out? Of course, I mean, our programs do a lot more than we do. They can also multiply and all that stuff. But the interesting point I'm trying to make is, I put this example because it's like very telling example. You were happily going along saying, this is these are subsets. This is a set of goals that I can achieve, or this is a set of goals I can achieve. Now imagine you are going with this. Okay? Then you will do lots and lots of actions below this, lots and lots of actions below this, lots and lots of actions below this. This one dead guy will have exponential number of dead descendants. The best way to do search, it turns out, is fail first. If you ever see a failing node, you should realize that it's a failing node. But it's easier said than done. To actually prove that a particular state cannot be achieved, in this particular case, had I told you that I need clear B and not clear B, then you would have said, yeah, of course you're being wishy-washy. There's no way you can have both of those. And in fact, you could realize that enough that you threw that into that particular statement. You'll never have a state directly, after one level, you'll never have a state which says clear B and not clear B. Why? Because that means this guy is actually violating one of the goals, and you wouldn't even have considered it. But then there will still be failing nodes. That's because it's physically impossible in this domain to reach this set of goals. In some other domain, that's possible. Do you see what I'm saying? If I had one extra block, I can be holding A and B can still be not clear, because that block can be on top of B. But in your world, it's not possible. It's too much to expect for you to figure that out. In the worst case, checking that a particular goal cannot be reached is doing planning directly. Now, since I said this, how hard is that? In fact, I never talked about complexity until now. Right? I mean, I didn't talk about it. How many of you heard of computational complexity? NP completeness, decidability, undecidability. Okay, so we are going to hear about it again today. Okay. In the worst case, how hard is it to solve a planning problem? I didn't ask this question for search. In the worst case, how hard is it to solve a search problem? Because many, many different kinds of problems can be written as search problems. And it could be any level of hardness. It can be, if I wrote sorting as search, it will only be polynomial. If I write theorem proving as search, that would be semi-decidable. Right? So you don't know. It's hard to answer that. But now I'm talking about a very specific kind of search problems, where the search problems where actions are written this way. And the initial states are in the initial, states have state variables. States are defined in terms of state variables. Actions are written this way. Now the question then is of, how hard is it to find a plan in this representation? Remember that computational complexity, I don't know whether you remember it or not, it shouldn't depend upon a specific algorithm. Whether or not a problem is hard, I can easily write double exponential sorting algorithm. And as we speak, today, there are people in Intel writing triple exponential topological sort algorithms. Because they just didn't realize that it was a topological sort, and they just wrote something, and that winds up being pretty darn inefficient. And you can feel smug, but they have a job you don't yet. So people can write bad algorithms when the problem is solvable, right? But that's not the issue. The issue is it at all possible to write a tractable algorithm for this? So in some sense, what is the minimum worst case complexity of any algorithm that would be solving this problem? It turns out we can answer this. And I won't go into the details, but it turns out that this is, for this representation, it is p-space complete. And what that means is it's as hard as the hardest problem that you can solve using polynomial space. And it's essentially assumed that p-space complete is harder than NP complete. Okay, now the reason that is the case, the reason it's actually p-space complete and not NP complete, again, this is another useful thing to understand. Again, as I said, this is sort of a carnivore course. It kind of is, gets insights from all the other things that you have done or may not have done. Okay, the reason, in fact, this is not NP complete and it's actually higher than that is for a problem to be NP complete. If I were to give you a solution and say, I think this is a solution, you should be able to check that in polynomial time. NP stands for non-deterministic polynomial. And the mental picture is some really, really rich uncle is spewing out all potential solutions. And they also bought you as many laptops as there are potential solutions. And each laptop is checking each solution's correctness. And if any of them finds a correct solution, it says, I'm done, and then you're done. So it's like the most crazy parallel computation. If you can solve a problem with this kind of a parallel machine in polynomial time, then it's called NP complete. It's a class NP problem. And NP complete is the hardest of this class of problems. Okay, so for it to be in class NP, if I give you the solution, you should be able to check whether or not it's a solution in polynomial time. Okay, now if I were to give you a solution here, how do you check whether it's a solution or not? You apply the first action in the initial state, compute the new state, apply the next action, compute the new state, and when you're done with all the actions, check if the final state is satisfying the goals. The total amount of work you do is proportional to the number of actions. So if I said that in fact it's a non-polynomial problem, because it's not in class NP, it must mean that there should be exponential number of actions for some problems. That's the only way it won't be NP complete. Do you see the reasoning? Okay, for it not to be polynomial must means just you know that you can check the correctness of a solution by just executing each of the actions in your head. And if there are only polynomial number of actions, then it should be done in polynomial time. But if it says exponential number of actions, even if you spend only 1 unit of time for each action, you will do exponential amount of time. So for this to be not NP complete, it must be because you can write problems in this representation for which the solutions are exponentially long in the size of input. You're computer science students. Tell me the most obvious problem you know which has exponential size solution. You must have done this somewhere.
Traveling salesman?
No. No. Traveling salesman, the solution length has to be just in terms of the number of cities. So exponential time solutions, exponential length solutions should be surprising to you because the solution is exponentially long in the size of the input. So you should be surprised. How many of you have heard of Towers of Hanoi problem? You see? Towers of Hanoi it's also been called the towers of Brahma. You are going to leave the class if you continue doing this. Okay? Towers of Brahma, towers of all sorts of things. Every culture has its own name for this problem, right? And the beauty of this problem is if there are n pegs, you need 2 power n moves to solve the problem. And it turns out that you can write Tower of Hanoi problem in this representation. You can do it actually. Maybe I'll make it a homework at some point of time. You should be able to write Tower of Hanoi problem in this representation. Which means problems written in this representation can have exponential size solutions. And all it requires for somebody to die in worst case complexity is that there is one problem that is going to take that amount of time. And since you can write Tower of Hanoi in this, it's p-space complete. That's one way of understanding it. It also kind of is useful because it tells you the sort of the expressiveness of this representation. It looks like it's a simple representation, but yet you can, in this representation, write problems which will require exponentially long solutions. Okay, that was a very long digression about how hard the problems here are. And the problems here are p-space complete, which is kind of harder than exponential, NP complete. And in particular, you don't expect, for normal domains in planning, you don't expect to do better than exponential time in terms of performance. Exponential length of the solution is different from exponential time of the performance. Even if you have polynomial length of the solution, you can do exponential time to find the solution. Okay. Anyway, so in this particular case, since it is actually searching in the 3 power, both of them you can see that both of these can take exponential time because this has a 2 power n states. If you have n variables, you have 2 power n states. So it actually can essentially spend 2 power n expansions if I make the problem such that the last guy is the solution. The last guy you wind up checking is the solution. Okay, and this guy searches in the space of 3 power n, so this guy can actually be worse. And the reason I actually got into this whole argument is, we kind of felt slightly silly that we didn't realize that this is a dead state. And if we realized that, we could have cut this off. We would have put it on the queue. Right? But it's not easy to realize that. If you want a sound and complete procedure which takes a set of goals and tells you, yes, they are solvable, no, they are not solvable, that procedure will have, in the worst case, the same complexity as the planning problem. Right? However, if you're only using it here, you can find a sound but incomplete procedure. For example, that means a procedure which, if it says this can't be achieved, they certainly cannot be achieved. If it says it can be achieved, it only means maybe they can be achieved. If I give you such a procedure, you can use that, and maybe you can cut a few of these kinds of nodes, you can improve the search. That's another way heuristics help. In some sense, if you have a good heuristic, you should have realized that this particular state is infinitely far from the initial state. That's what pruning of it, that basically allows you to prune this particular node. Okay? Okay? So let's just, since we are here, let's also do, I'm going to remove this and I'm going to do a regression example. Since I wrote it there, and since I'm not going to, this is actually relevant for your exam, so I want you to make sure that you understand. Okay, so I want to do this problem, but for regression now. Okay, and then I have similar problem in the homework that I gave you that you can try when it won't be graded. Okay, so I'm starting with RS. Okay, can I do A1 as the last action? Remember, one way to do it is put it this way. A1 should be the last action. Can I have A1 as the last action? No. If any of you think it can be, then you haven't yet gotten it, right? Because if A1 is the last action, then its effects should be consistent with R and S. But A1 will give you not S. So A1 cannot be done as the last action. Right? Okay. Now, can I do A2 as the last action? Because A2 will give R and J. Is R and J consistent with R and S? Yeah. Because the only thing that's common is R and they both agree. That's fine. Okay? And then, so that is one part. That is, it is actually it's not doing any harm. But is it doing anything useful? Yes, because it's giving R. Right? So then it wins on both counts. So I will put A2 in. And then, now since A2 is giving R already, then I will write S, which is not yet done. Then do I write J? Do I write J? I'm just doing the mistakes that people will do. Okay. But J, obviously, just because A2 gives J, that doesn't mean that you should now start needing J. Right? You don't need it, you know. So A2 will give J whether you like it or not, but that's fine. You know, I mean, it is required. It is giving R, so I won't have to work on R, and it is not giving S, which you required, so S will be brought down. And then to be able to do A2, you need M. So you throw in M. Right? Okay. How about A3? Can I do A3?
Yes.
Yeah, because it does give S, which is useful, and it's not killing either R. I mean, it's not killing R. Right? So I can give A3, so it also again succeeds. And so in this case, it gives S, and so it needs R. I mean, you still need to work on R. Okay? And then, because you are getting A3, you now have to get Q. So you have like, think about it this way. You have two homework problems, right? And you have two friends. One friend can give you one homework problem, but will mess up your understanding of the second one. You know, the other friend will do the second homework problem, but mess up the homework, your understanding of the first one. A third friend will do the first homework problem and doesn't do anything about the second homework problem. So who would you call? Third friend. And the fourth friend will just come and watch TV. Right? You won't call unless you really like this friend. Okay? Right? Now the interesting thing, of course, is if you call a friend, they might want pizza. Originally, your goals were to just do the homework and be done with it. Now, because this guy is showing up to help you with the homework, you need to buy this guy pizza. That wasn't part of the goals before, but he's not going to do homework unless you give him pizza. So now you are out looking for pizza. That's exactly how human reasoning works. You know, I have top-level goals, I'm trying to make them true, then after a while you don't know what the heck you're doing because you're like, you know, why am I looking exactly for change? Because I needed to tip the pizza guy and I don't have change, and so now I go to the bank to withdraw cash, and I would be thinking, shouldn't I be doing homework? Right? Okay, but thankfully planning is not execution. Planning is all in thinking. Okay, when you are actually executing this kind of totally ridiculous plans, then your planner failed you. Right? Okay? So that's our cue. And then what can I do now? So at this point, you know, just to show one thing which will work, if I had gone from A2, and then if I were to do A3 from here, if I were to do A3 from here, then I can do A3 because it gives, it says, it gives S, and it's not killing M. So what it's doing is not inconsistent. Right? Okay? And so what I can do is I can give A3, and if A3 is done, you know, S is no longer, and in fact it's giving S and M. Right? I'm sorry. So then I just basically have none of the goals from the top level that are needed. The only thing that is required is Q, because this guy needs Q. Now Q is true in the initial state. So when I pick this state, I'll say I'm done. And my goal, my plan is what? Is my plan A2, A3 or A3, A2? A3, A2. That's why you should use the arrows. Progression put the forward arrows, regression put the backward arrows. And then you'll be fine. You'll never get confused. That's regression. Okay? So, and then as I said, the progression between, I want you to understand both. They have trade-offs, but neither of them are necessarily winning yet, because regression has a much lower branching factor, but it generates dead states. And you could be expanding dead states without realizing they are dead. And so one of the worst things you can do is to keep working on a fruitless, already dead path. Okay? Eventually you will end. And in fact, one of the more interesting things is, you should ask, I'll get you. One of the more interesting things is, if I did not realize that this is dead, what will happen to me eventually? You will realize that at some point of time you will generate nodes, none of which have children. Why? Because the only way they can have children is to use an action which will kill one of the, which will be inconsistent with one of the things that they have. Do you understand what I'm saying? And so then you will eventually lead to a set of states, none of which have children. If they don't have children, eventually you will come back to the other branch, even if you're doing that first. Right? That's how it actually still will be complete. Yes?
I don't know if I missed something, but didn't you have initial state was 3 different states there, and all you have is Q for your...
What initial state is what?
upper
Okay,
left.
that's a good question. So my initial state has P, Q, S true. In fact, that's not the only thing. In my initial state, P is true, Q is true, S is true, J is false, P is false, M is false, R is false. That's what my initial state is. Okay, now the very important thing to remember is, when you're coming backwards, this is your wish list. This is not what you want the entire state to be. This is your wish list. If I give you a state where Q is true, you are happy. Initial state does have Q true. Again, it's a very reasonable way to get confused the first time you hear about regression. And the way to understand this is, we are not talking about, this is not a complete state at all. This is a partial state. It's like the goal state standing. And if whatever you need is already present in the initial state, you're done. And by the way, I wrote this picture this way, right? Clear B, not clear B, hand empty this way, and on table this way, and I put the progression this way and regression this way. In fact, you can do, if you're into it, bidirectional search. You can start searching from this side as well as this side. And then you will be done as soon as anybody on the fringe here is satisfied by anybody on the fringe here. It's sort of like some electricity flows and the path is completed. Then you just read the path of you. That's bidirectional search. You don't have to just do progression or regression. You can do both. Okay? Any other questions? That's a very good question, by the way. I mean, the more you think about the questions as I'm talking, the fewer you will have to go back into cycles. And for that, you have to avoid watching your cell phones and listen to me. That's the only way. Otherwise, you will figure this out later, after wasting the class time, because I made you come here. Yeah, any other questions? Okay, so this is about progression and regression, and you understood how the search works. This part you should understand. This is actually required for the exam too, because I assume that, as I said, everything I do until the end of today's class is fair game. Okay, now I'm going to start working on heuristics now. Okay, which is basically, remember, we're doing now search in the space of states with structure, right? And I kind of told you that because the structure is there, you could do nifty things that you couldn't do with the child generator function, for example. How do you ask the child generator function to generate states in the reverse way? It's not obvious. Okay, but now you could do all that. Now the question is, can you do that also for heuristics? And in fact, this part of the topic will end with what's called the planning graph heuristics, which, if you looked at the chapter you heard, you at least read that. And then, that's what I'll be doing tomorrow mostly. But today I will get to why that is useful. Okay, why do you need that kind of a heuristics? And the idea is, we'll start with, again, a simple heuristic, just as for for a puzzle, we started with number of misplaced tiles. And then figured out that's not as good, and then talked about things like pattern databases. Except now we have a much more interesting terminology. This is sort of terminology we can understand, such as goals and sub-goals, right? And so we can actually talk about what are the properties of heuristics in terms of goals and sub-goals. And first you'll figure that out, and then tomorrow we'll talk about planning graph heuristics, which actually have those properties, okay? And in particular, I want to actually show, using this as the whipping boy, that this is a bad heuristic. That if you just count the set difference, that's a reasonable heuristic, but that's not a good heuristic necessarily. Okay, so first of all, let's make sure that we understand what a set difference heuristic is. A set difference heuristic is the number of goals that are not yet satisfied. Okay, so if you're going in this direction, here, how many goals are not satisfied? This is your wish list, S and M. Okay, S is already satisfied in the initial state. M is not. So its heuristic cost is 1. If you take R and Q, R is not true, Q is true, so its heuristic cost is also 1. If you go in the forward direction, the same situation. So you look at the top level goals and see if they're all already present in the current state. If they're all present, then there are 0 goals that are not satisfied. That means heuristic cost is 0. And if you have heuristic cost 0, that means you're dead. You're dumb. Not dead, I'm sorry, you're dumb. Right? So you should be really happy. Okay. So the question then, so that's your set difference. You know, you're taking the difference. You're thinking, you're acting as if these states, which are basically conjunction of variable values, you're acting as if they're sets. You're just deciding the set difference. Elements that are present in one that are not present in another, and the cardinality of it. Okay, so that's a heuristic. It's not a bad heuristic. My question is, anytime you hear about heuristics, since we developed all this crazy theory about heuristics, you know, admissibility, informedness, we should ask ourselves, does this have those properties? Okay, so in particular, is HSD informed? Now I'm calling HSD means heuristic, set difference heuristic. Is it informed? That means does it estimate the path cost well? And the second question is it admissible? In fact, maybe both of them are important questions. This question is it admissible? That means, is it guaranteed to underestimate the cost? If it's not informed, that means it's underestimating too much, sometimes. If it's not admissible, that means sometimes it's not underestimating at all. Do you see what I'm saying? So this guy is bad. If you lose both these properties, that is because most of the time you underestimate too much, but there are a few times where you don't underestimate at all. And if you don't underestimate even for one case, you're dead in terms of admissibility. Can anybody see whether set difference heuristic is admissible, first of all? Why not? Give me a reason. So to talk about admissibility, you need a proof. To talk about not admissibility, you need an example. Yes?
If you had an action that satisfied, say, 3 goals at once.
Do you see what he said just now? If an action satisfies multiple goals at once, and you are assuming each action costs 1 unit, and if this particular state currently has 3 goals missing, you assume its cost is 3, because you work on each of them separately. But if a single action gives all 3, which is very much possible, then you are overestimating. Okay, now, here is an interesting thing that I want you to think about. If you have goals like that, where all your goals can actually be satisfied by just one action, I will give you 3 words that probably, they have intuitive meanings for most of you, and we'll actually make it precise in a minute. But I'll say sub-goals can be independent. That means, it's like these goals have no connection with each other. Making progress on one goal doesn't change your progress on the other goal, and vice versa. Okay? Positively interacting and negatively interacting. his example, are the sub-goals independent? Of course not, because you could do all of them at the same time. So there is interaction. Is the interaction positive or negative? You guys see that, right? If you can somehow do 3 goals for the cost of 1, it must be positive interaction. They're somehow getting along fine. Okay, and HSD wound up being inadmissible because it missed that positive interaction. Because it misses positive interactions sometimes. It just assumes that everything is sort of independent. Okay, because when you're counting just the number of goals, then it's sort of the implicit assumption is they're all independent. So each goal will take the same amount of time to produce, to work on. Okay, so HSD is becoming inadmissible because it is missing positive interactions. Okay, so would HSD be admissible if all your goals are independent? If I tell you that in your problem the goals are all independent, then yes, right? So for example, one way you can generate easily independent problems is you have one class goal and one home goal. And normally they are sort of independent. What you do in class and what you do in home are different, and so basically they're independent. Okay. Anyway, so HSD is not admissible. You agree with that right now? Now the next question is it informed, in the sense that does it reasonably estimate the amount of work to be done? More importantly, actually, one of the very interesting questions is this negative impact. One of the interesting questions is, so suppose I have 2 sub-goals, right? I needed, so I wanted an iPad and a cover for the iPad. Okay? Use your common sense. Okay? So here is a state where I have iPad but no cover yet. Here is a state where I have a cover, no iPad. Use your common sense, which is according to HSD, both of them are equally bad, are equally good. Right? Right? What do you think? Right? Because having a cover, everybody has a cover. It's like, to be able to eat, like, let's say, lasagna, you need a fork and lasagna. Everybody has a fork. Very few people have lasagna. Right? Having a fork doesn't help. Having a cover doesn't help. Okay? So, in fact, not all goals are created equal. So, just counting the number of goals doesn't make sense. Okay? So, in this particular case, all of you assumed, of course, that which one is better? All of you assume which one is better? The one having iPad and no cover, or the one having cover and no iPad? iPad and no cover is better than having no cover and iPad, right? I'm going to Taiwan tomorrow night. And so I was searching for stuff on Taiwan, and this article popped up. Beautiful article. So back in 2010, apparently, Taiwanese government has not yet okayed tablet PCs to be sold in Taiwan. And yet, tablet PCs are available. And so you cannot legally sell them. So this article goes on to say that people were selling tablet PCs, basically iPads, by saying iPad is free, cover is $4,000. Okay, of course, they made it such that you must buy both. Otherwise, they would basically be just having a whole bunch of covers. So I mean, I thought it was cute because this example just almost it's opposite of they've changed this because everybody would think free iPad, let's all run, and then they will then throw this cover is $400 at you. Okay, but anyway, so that's kind of the other part. But so. First thing that we want to realize, the reason HSD is not all that great is because it assumes that all sub-goals will take exactly one action, but a single sub-goal can take a large number of actions to achieve. In this particular case, I was sort of, in this case, I'm thinking in terms of costs. But even if you're thinking in terms of actions, right? For example, get an A in the course and, have a coffee. Those are two goals. Right now, you don't have a coffee in front of you, and you haven't yet gotten an A in the course. Okay, but obviously, I assume that getting an A in the course will require a lot more actions than getting a coffee, or I'm doing something wrong. Okay, and so clearly, and one goal can have a much longer plan than the other. And if you just assume all goals are equally costly, you make mistakes. A second, a more subtle issue, which is not obvious upfront, is sometimes you can get either of the goals, but you can't get both of them. Or if you get both of them, you pay a lot more. How many of you seen these Visa commercials? Getting to Ireland, $100, going to the bar, $300, and making your mother happy, priceless, right? So basically, they're saying, there are interesting interactions between goals. Okay, in this particular case, I can, for example, in the blocks world, if I have a goal, hand empty, cheap, whatever I have, put it down. If I have another goal, hand full, that also is cheap. Pick something, a handful. Now I have a goal, hand empty and hand full. Dead. So here the goals have interactions. And in general, your life is full of interactions. Have fun yesterday night. Get done with homework by today's class. Negative interactions galore. Unless, you hopefully train yourself such that you get fun by doing homework, which I'm hoping you will do. Right? Otherwise, essentially, you have negative interactions. Too much fun, no homework. Too much homework, no fun. Right? So life is full of negative interactions too. And because HSD misses negative interactions, it loses informedness. And because it misses positive interactions, it loses admissibility. So we have the situation where HSD is neither here nor there. It's an easy idea, but it doesn't work very well. And I will end with this one slide. Basically, you don't need to get much out of it other than to tell you, let me see, not this slide, this one. I drew this once on the board, right? Now I drew it in color. Okay, so this is cost of computing a heuristic. This is the cost of doing search if you want to compute that heuristic. This is the total cost. HSD is on this side. It's very easy to compute, but most of the time the search time will be quite large. And we'll talk about heuristics, tomorrow. Of course, you can also do H star, which basically just solves the problem for every state and uses the optimal plan from every state as the heuristic to solve the original problem. That would take forever, a lot of time, but then once you have that information, you have H star and you do very little time doing search. Okay, what's interesting is, as I mentioned last time, most of the time people sort of felt that this minimum is likely to occur to this side. So people are always looking for heuristics which can be described in one slide. That's what I did, HSD, anybody can understand. Whereas I'm telling you that I'm going to spend tomorrow's whole class to explain just one heuristic. That shouldn't be easy. If I'm taking that one full class to explain, that means it'll take some time for you to program it, for example. And yet what matters is it actually, somewhere here, for example. So it turns out that the planning of heuristics kind of falls somewhere in this region. So they take actually longer time to compute, but the search with them is significantly better than search with either this or with this. And one of the interesting points is in the past, in planning, in these kinds of problems, people used to draw this kind of curves, saying, to do, let's say, 3 blocks, it starts taking too much time. So everything is exponential. So if you drew this in your paper, that's because hopefully you realize that your system is this. You won't write a paper to say that my system does worse than other people's systems, right? If you put this in your paper, that's because this is your system. But your system is better than other bozos, but it's just pretty bad. And with heuristics like planning graph that we'll be discussing tomorrow, it's not just a magic. That's not the only magic. It's basically the idea that heuristics can take more time. With that, the scalability has increased like significantly. You can do previously, let's say, 10 action plan. You can do 10 action plans maybe in minutes, okay, or even hours sometimes. And now we can do hundreds of actions plans in seconds. Now you can say, well, that's because Bill Gates has been hard at work, improving the Windows operating system. You didn't believe that, right? But but even taking that into consideration, remember the greatness of exponential search. If you were to speed up your computer twofold, and if your original problem is taking 2 power n time, and you are able to solve a problem of size 5, and you doubled your computer power, you can now solve the problem of size what, 10? Size 6. If you could solve a problem of size 100, you can solve a problem of size 101 after doubling the computer power. That's why I said 2 power n should be the nightmare scenario for computer scientists. Okay, and so in fact, it's not just because computers became faster, it's because we became smarter. And we have realized that good heuristics can actually be here. It might take a whole day to understand it, but then they will actually do better in practice. So come back tomorrow, I'll explain that.